elevator in the ground, that means the elevator is sitting on the ground, as opposed to actually moving up and down through the shaft.
Okay, I thought it was on, okay.
Oh, no,
Okay.
no, sorry, I didn't draw the ground here, but we
Okay.
assume that. If it had been sitting on the ground, absolutely, but elevators traditionally don't. I think that's. Sorry, my mind went to the mangled corpse that would be in the bottom of the elevator if it were on the ground. But there are safety protocols in elevators so that if the cable broke, it doesn't plummet like it does in the movies. Unless, of course, the bad guy blows up the safety protocol or the safety mechanisms. Elevators are fine. And all physics leads to death. Brittany, yes?
So it's telling us to rank from greatest to least the following quantities at following floors, two, five, second and fifth.
All right, is the elevators going up or down? I forget. Going down from, so it starts at the 10th floor. So it's going down, so it is accelerating, so it's picking up speed here. So it's speeding up. And then at the 8th floor to the 3rd floor, it's constant. And then third, it slows down. Here we go. All right, so we obviously have concepts from two different things here. We have the whole speeding up, slowing down aspect, chapter 3, and then we have forces involved, which is chapter 2. And we bring them together in chapters 4 and 5. So in terms of ranking, one of them was, I think, his mass, his weight.
His mass, yeah, his weight, the magnitude of normal force he exerts on the scale, and the magnitude of normal force he exerts on the elevator.
All right, so let's do that, the last one. We'll just, the normal force that he exerts on the elevator. Which of these arrows represents the normal force he exerts on the elevator? But that one?
Oh, the elevator?
Yes.
But he's on the scale.
Yes, he is. So the last question deals with the normal force he exerts on the elevator.
Okay.
And so, what is the normal force that he exerts on the elevator?
0?
Yes,
Okay.
because he's not touching it.
I thought I was missing something.
No, and you were thinking way up here, you needed to bring it down.
Thank you.
All right, so that one, he's not touching the elevator. It's a trivial question once you recognize that.
Okay.
All right, his mass. What do you know about the mass of an object as it moves?
Force is mass times acceleration. Well, what do I know about this?
If I magically appeared on the moon, what would happen to my mass?
Oh,
It doesn't change.
I guess you missed that?
I didn't hear what you said.
Okay, we'll try that again. If I suddenly snap my fingers and appear on the moon, what happens to my mass?
Oh, it doesn't change.
So as he's riding up and down an elevator, another one, once you recognize that,
Okay.
it's trivial. The non-trivial one's coming up.
Okay.
His weight. What's the formula for weight?
Mass times gravity, or acceleration due to gravity.
Thank you very much for correcting.
I knew that was gonna come.
So it's his mass times the acceleration due to gravity. So his mass isn't changing, we just established that. Is the acceleration due to gravity changing over these 10 floors?
No.
You're both right. So
A little bit.
I thought I changed the wording to eliminate one of those. Thank you. And a scale, closed door. Yeah. Apparently I did not. There's one version of that I was thinking where I put in about assume that G is constant the entire time. So, for practical purposes, this G does not change, so therefore mass doesn't change, G doesn't change. But you could also make the argument that as he gets closer to the Earth, the value of G does increase a little bit, as Aiden said. So, in that respect, that would be part of your explanation, that you're closer to the planet. Now, the difference between G here and the G here, you would need multi-million-dollar equipment in order to be able to detect that difference. It has been done. It involves lasers and shifting of the spectrum because of the warping of space and time. I don't know how they do it. The general relativity kicked my butt, so.
Okay.
And then the last one is the force that he exerts on the scale,
Yeah.
or the force that the scale exerts on him.
Normal
He
force
exerts.
he exerts on the scale.
And he on the scale, all right. Well, the force that he exerts on the scale has got to be the same as the force that the scale exerts on him. So this is the non-trivial one. So I'm basically comparing these two right here. And this comes down to the acceleration, which brings us back over here. If he's accelerating upwards, which of these two is bigger? Yes. If he's accelerating upwards, that means that acceleration is up, and therefore the total force has to be up. If he's accelerating downwards, which of them is bigger? I heard it over here. That one would be. So now, over here, as he's descending and speeding up, what is the direction of his acceleration? When the velocity is constant, what's the direction of his acceleration?
Zero.
0. Constant velocity, acceleration 0. And when he's slowing down, what's the direction of his acceleration?
That's like, because he's slowing down.
Still didn't hear it.
It's wrong, I know it's wrong. It's negative because he's slowing down?
He's
Speed does not go negative.
We haven't established a positive or negative direction, so. But if you're slowing down, his velocity's gotta be downwards, because velocity is the direction of movement. If he's slowing down, is the acceleration in the same direction or opposite direction? So in the last phase, as he's slowing down, the acceleration's up. Or think about it this way, as you fall, or jump off a cable, make it as violent or as calm as you want. As something falls, in order to stop, there's gotta be something that pushes it in the opposite direction. Or pulls it in the opposite direction. If you were bungee jumping, and you jumped off right there, so you basically are in free fall for a bit, and then once the cord gets tension in it, I think you would feel yourself suddenly a whole lot of pressure on your chest if you're face down, or obviously never bungee jumped, so I'm not quite sure what your orientation is when you get to the bottom. Anyone know? Are you upright, face down, chest down?
What you said, sir?
When you bungee jump?
I've never done that. It depends how you want to get thrown.
Oh, okay, you have a choice?
You can
Okay.
sit down and stuff on a chair.
You feel some force from below slowing you down, I hope. If you're not, then I guess at some point you will very much. Well, actually, I don't know if you feel it or not. I hope never to find out. Anyway, I think I've answered your question, Brittany. Do you have a follow-up?
I understand now, but I think I'm not missing things and I'm just overcomplicating it, yeah.
Yeah, physics loves being overcomplicated.
Would those same rules apply like in the ocean? Like
you float back up and you fall into the ocean? Is that what you were like saying?
The bigger complication is if you, with the ocean, you have an additional force that's not covered by F-down, it's called a buoyant force, which tends to, as long as you are less dense than water, will actually scratch that. In any fluid, there's a force upwards.
That applies to air too, right?
Yes. And there's a video, I can't remember if I posted it for 110. It'll be in the chapters that we're skipping, but I go through far more complex analysis of the difference between what the scale measures and the weight. If you bring buoyant force into it, you got another force acting upwards on you. Depending on where you are on the earth, as the earth is spinning, you've got another force acting, or you have another imbalance, I should say. So there's actually, for me, I think about a 4 Newton difference between my weight and the normal force if you take into account air pressure and spin of the earth and where I am on the earth. Yes?
B on number 1. I don't understand this.
So this was, you've got a mass, you push on it, and then you do it on the moon? Is that where I did it? Okay. Other questions on this before I erase it?
I guess, did you give us like a constant for B, or is it just the underneath the?
Oh, for a constant for G?
Yeah.
I didn't, it's just a ranking thing, so you don't actually need a number, but you can make a value up for G if you want. And I'm assuming, well, it's recorded also. All right, so for number 1, I believe you're pushing on the horizontal frictionless surface. And this was 100 newtons and 70 kilograms. Hey, let's do a force diagram. Got ground, I got mass. All right. And I have F-down. I think somebody just said something. Maybe not. Like, what force is acting on what and in which direction?
Friction. Oh, you said friction, sorry.
I believe so.
Sorry.
All right, well, that eliminates friction.
No tension.
Okay.
There is other.
There is, in this case, that's the 100 newtons. And there's some mystery object out there where the 100 newtons pushing that way, but we don't need to draw that.
Way down on the box and up on the ground. Normal force, up on the box. And down on
All right. What do you know about the weight and the normal force there, besides they're in opposite directions?
They're equal.
In magnitude, yes. They cancel each other out. This box is gonna move horizontally. So this is, I think, a 70 kilogram. So the acceleration of this box, that's for part number 1, we're just plugging straight into F equals ma. I know the force. I know the mass because that's given, so just solve for A. Now, we take this to some other place. I believe the moon, but it could have been Mars, Venus, any other place. I set it up. How does the force diagram change if I put it someplace else? Yeah, the force diagram though. You're right, force of gravity would change. What else would change? In terms of numbers.
The weight.
That's the force of gravity. If the weight is cut by a factor of 7.
Well, yeah, if the
So
weight
the
changes.
bigger the push, or?
Like, sorry,
The
Brittany?
mass doesn't change.
Correct.
Okay. And the force doesn't change either.
You mean the 100 Newton?
Yeah.
What about the normal force?
Would it cancel out?
So what does that tell you about the normal force?
It's the same? Is it the same?
As,
The weight?
yes, it'd still be the same as the weight. So both, the weight would change, the weight would, if I'm going to the moon, the weight gets cut by a factor of 7, the normal force would also.
Why do you make that so complicated?
I thought you actually said the right answer as Brittany was talking. I was giving you credit for it, but maybe not. So these still cancel each other out. So we still have a total force of 100 newtons acting on it. The mass hasn't changed, as you said. So I think the question was, I forgot what the actual wording of the question was.
How would the results change when I conducted on it?
Yeah, and the result is, in other words, the acceleration. Therefore, Brittany, I think you're overcomplicating it.
Okay, yeah, I mean, I've had, yeah, okay. Gotcha.
If the total force stays the same and the mass stays the same.
Yeah, that's what I had. I didn't know
Okay.
what y'all were talking about 7, though, like.
Oh, if you go from the Earth to the Moon, your
Yeah.
weight gets cut by a factor of
Right.
7. That's what I was talking about there.
Okay, I thought that had something to do with the, way you get the answer or something. Okay,
No,
I'm good.
just bonus knowledge. Other questions on this? Other questions?
Yeah. So, what I did, because to do number 1, I was looking at my notes, right? And I ended up grabbing the 100 and dividing it by 70.
Okay.
And like, I saw that you didn't do that, so.
Oh, I didn't actually finish it, but, so, the force is 100 newtons. The mass was 70 kilograms times the acceleration. Let's have it that way, it's positive. So the math problem is 100 is equal to 70 times A, that's the math problem. And you would solve it exactly what you did. Thought it was unlocked. Okay. That's a 70. Just make sure you have the correct units at the end.
And that is gonna give us the acceleration on the Earth?
Yes. Or actually, anywhere.
Okay.
Gives you solve the problem. Other questions? Or other questions?
No, I was looking at the one who was talking about crouching down and jumping up.
Right.
And I was actually supposed to be doing that. I don't know, one second, let me read it again, 'cause I don't think it's. Cause I read something before, I was like, oh, I missed the word.
All right, well, she's checking that. Any other questions?
So,
Yes.
I'm all right with that, I'll do a force diagram and help him with that.
Okay.
Is that a good idea for number two?
Yeah, I mean, it basically, it still comes down to, you have two main forces acting on the person. All right, other questions?
I have a question about the lab.
Yes,
So I was doing the back of all these.
yes,
and I
that's a
got
bunch
really,
thing.
really confused.
You were the first person ever, maybe not. Yes,
If you can like work through maybe one of them, just to
Okay.
be sure that I'm on the right track.
anyone in particular?
Number 17, which is acceleration that is not constant and constant scalar acceleration.
So acceleration that is not constant, but the scalar acceleration is constant? Okay. Alright, so acceleration, not constant. Acceleration is constant. Right. What has to be taking place if this acceleration is not constant?
As we speed or direction is changing, well, velocity is not constant.
Okay. So, wait, what was the last thing you said there?
Me?
Yes,
The
Brittany.
Velocity is not constant, it's changing, so speed and direction.
Yeah, I was gonna nitpick, but no, that still comes out to the same place. Elaine, you had said something? I thought?
I did,
Aiden?
I lost